In this video, I want to show you a couple examples of ion complex problems. In this problem, we're asked to determine what the equilibrium concentration of copper ions is after adding 0.001 moles of copper nitrate to a 1 liter solution of 1.5 molar ammonia. The formation constant of the complex is very, very large. It's 2.1 times 10 to the 13th. And you could ignore the nitrate in the copper nitrate because it plays no part in the reaction. The copper nitrate is simply a source of copper ion. So the initial concentrations, as laid out in the ice table, are 0.001 molar copper ion. It says 0.001 moles of copper nitrate. We could assume that was added by a small amount of solid, and that small amount of solid did not change the volume of the solution. So if there's 0.001 moles of copper nitrate, there's 0.001 molar copper nitrate in that liter. And then the molarity of the ammonia is 1.5 molar to start out with. The change is going to be the loss of the copper ion and some amount of ammonia ion. And we could start off by approximating that to be 0.001 for both. And we add 0.001 molar of the copper ammonia complex. In the equilibrium line in the ice table, it's a bit unconventional because I have a plus x and a minus x. The pluses and minuses are typically shown in the change line in an ice table. But we need to account for some amount of copper ion that remains at equilibrium. The copper ammonia complex forms, but there is a reverse reaction to provide some free copper ion. So we need to show that, and we're showing that as an X. And because the formation constant is so large, and the concentration of ammonia is so large to start with, and the initial concentration of copper ion is so small, we could assume that the equilibrium concentration of ammonia is 1.5 molar. And also we could assume that the loss of the copper ammonia complex to form the free copper ion, this loss of minus x, is also negligible based on what I just said about the concentrations of each of these ions. So as we substitute these terms into the equilibrium constant, we could ignore the minus x, 0.001, minus x simply becomes 0.001, and then we need to account for the copper in some manner, so that's got to be the x, the unknown, and the amount of ammonia at equilibrium, we could simplify this as 1.5. And of course we need to raise that to the fourth power because of the 4 in the chemical equation. After substituting the values in and solving for x, x is equal to 9.4 times 10 to the minus 18th. And that seems reasonable based on the small amount of copper that we start with and the very, very large formation constant. In other words, this is highly, highly product driven. The equilibrium will be established with a lot of product and a very, very small amount of reactant remaining. In this case, the copper ion. In this problem, we're asked to determine the silver concentration in the reaction between silver and ammonia to form a silver-ammonia complex. The formation constant is, again, extraordinarily high, very product-favored, although these are not completion reactions. Remember, these reactions attain equilibrium, so we need to account for some amount of reactant remaining at equilibrium. Okay, so the initial concentrations of silver and ammonia are 0.005 and 1 molar respectively. Like the previous problem, we could assume the silver nitrate, the source of silver, was added in the form of some solid, and the amount of that solid that was added is a negligible change to the total volume of 1 liter. So if there's 0.005 moles of silver nitrate, we could assume that the molarity of the silver is 0.005 mole per 1 liter, or 0.005 molar. And the molarity of ammonia doesn't change due to that negligible change in volume. Okay, so then the change, I wrote slightly different than the previous problem in that I showed the loss and then the gain back of the reactants due to equilibrium all in the same line. we know we're going to lose silver. And let's first assume we're going to lose all of it because it's highly product favored. So loss of 0.005. But then we're going to gain some back because of the equilibrium that is attained. So that's where the plus x comes from in this line. Regarding the ammonia, we're going to lose twice the molarity of the silver because it's a 1:2 stoichiometry. So we're going to lose minus 2 times 0.005 or 0.01 molar. But then we're going to gain back some after equilibrium has been attained. And what we're going to gain back is not x but 2x because of the stoichiometry of the 1:2 between the two reactants. Okay, on the product side, we're going to form quite a bit of the complex. So we could initially assume that will form 0.005 molar. But then we also need to think about the tiny amount of loss that we're going to have due to equilibrium establishment. Lose some amount of the complex, and we're going to represent it as x because of the 1:1 stoichiometry between the silver and the silver ammonia complex. Now to simplify the math in our equilibrium constant expression, we're going to enter 0.005 molar as the concentration of the silver ammonia complex, leaving out the minus x. Because this is a highly product favored reaction, so the amount that is lost from x, this minus x, is really small. And it's negligible compared to the amount of product that was formed. So we could simplify the numerator by simply entering 0.005. With regard to the denominator, we need to have an unknown represented in the equation. So we need that as our x, and the unknown is the silver. And so the silver appears in the denominator. And so we have the x here representing silver. And to simplify the math, again, we're going to approximate that the concentration of ammonia in this case is 0.99. But where did that come from? Well, take a look at the change line. Minus 2 times 0.005 is really minus 0.01, and then we have this plus 2x. So 1 minus 0.01 is 0.99. Now, I could have written 2x here because we're going to add this cell and this cell, but that 2x, that additional amount of ammonium formed due to equilibrium, is reasonably negligible compared to the amount of ammonia that we started with. These approximations are all done to simplify our math. So we could drop the 2x for ammonia. This is 0.99. You need to square the 0.99 because there's a 2 in front of the ammonia. X is our unknown concentration of silver, and the silver ammonia complex is 0.005. After doing the math, turns out that the concentration of silver, which is x, is 4.63 times 10 to the minus 10th. And that seems reasonable because of the highly product-favored equilibrium of this reaction.